Solving problems with frequency. For example, let's say we have a wave and it's traveling along and has a wavelength of 2 meters. And for this wave to pass a point, it takes a time of 2 seconds. So we know frequency, since we're talking about this one wave, is 1 over 2. So frequency is 0.5 hertz. We know 2 meters is our wavelength. So velocity is equal to wavelength times frequency, which is 2 times 0.5, which is 1 meter. Another way to look at it, let's say we have a sound wave. We have a tuning fork, and the tuning fork is at a frequency of 291 hertz. We know velocity of sound at room temp is 342 meters per second. So what is the wavelength of the sound being emitted by pushing the air for the tuning fork? So we know velocity is equal to wavelength times frequency. So 342 is equal to wavelength divided by, or multiplied by 291. So that means wavelength is equal to 342 divided by 291, which is, looking at it, we know it's going to be more than 1, and it is. It's 1.17 meters. So that wavelength is 1.17 meters for a tuning fork of frequency 291 in a room at room temp. Now let's look at a sound wave. It's traveling at 342 meters per second. And we determine the wavelength to be 0.6 meters. What is the frequency of the tuning fork that's producing that wave? Well, we know velocity is equal to wavelength times frequency. 342 is equal to 0.6 times frequency. So frequency is equal to 342 divided by 0.6, which is equal to 570 hertz. So if we had a 570 hertz tuning fork at room temperature, it would produce a wavelength of 0.6 meters.